Hello and welcome back to A Slice of Physics. We're going to continue our discussion of the parameters of circular motion in this video, and we will discuss angular velocity, which is a new term that you're meeting. We'll relate that to the regular old velocity that we've been working with so far, and I will call that linear velocity to distinguish it from its angular cousin. Let's use the same examples as we did in our previous video to discuss these new concepts. So here's my wristwatch. I've got the hour hand, minute hand, and we're interested in talking about this second hand. And let's say the length of the second hand from the center to the very tip is 1 centimeter, and that would be then the radius of the circle it sweeps as it goes around. In our previous video, we discussed that time period for the second hand is nothing but 60 seconds. That's how long it takes to make one full revolution. So that was a period of circular motion. And there was a related concept of frequency, which was just 1 over t, which turned out to be 0.0167 hertz in this case, as we saw last time. So next we want to find the angular velocity of this second hand, and so let me introduce the concept of angular velocity over here. So we got angular velocity, and that's denoted by the Greek letter omega. It is a vector, as the name suggests, and that's defined as the angular displacement over the time duration it takes for that displacement. So just like linear velocity was the linear displacement over the time duration, angular velocity is the same just for the angular motion rather than the linear motion. So let's take the example of a second hand that sweeps from the number 12 at the top of the dial to number 2. And so in doing that, it's sweeping across an angle of this much, and that's what we would call the angular displacement, delta theta. And let's say it takes a time duration of delta t to do that. When we divide delta theta over delta t, you would get angular velocity. And by the way, since I've introduced these things as vectors, let me talk about the sign. Delta theta, angular displacement, by convention is defined to be positive for counterclockwise motion and negative for clockwise motion. So in this example, because this is a clockwise motion I took, this delta theta would be a negative value. And when I divide that by delta t, since delta t is always positive, omega would also be negative. Angular velocity would be negative for clockwise and positive for counterclockwise motion. Now let's take a special case, and I'm going to take a counterclockwise motion now. Let's say something swept a 1 full circle in counterclockwise motion. What is its delta theta? The delta theta would be this full angle, and positive because counterclockwise is positive. The full angle is 360 degrees or 2 pi radians. And how long it took to do this is what's defined as the period of the motion. So that's capital T. So the angular velocity would be 2 pi over t in units of radians per second. Radians for the 2 pi and second for the t. So the general definition of angular velocity, which was any angular displacement over its corresponding time duration, is equivalent to 2 pi over t, capital T, in units of radians per second. And as a last step in this conceptual discussion, let me introduce a relationship between linear speed and angular speed. By the way, omega without the vector notation would just simply be the angular speed, and that's simply the absolute value of the angular velocity, so we ignore the sign and just take its magnitude. So if I have a situation where I got this second hand and I want to see what the speed of a bug is as it's sitting on the very tip of this second hand and taking a ride for this full circle. So for that ride, the distance covered would be this circumference of the circle, which if its radius is r would be 2 pi r. And the time duration is simply the capital T, the time it takes for one full circle. So the speed of something sitting at a distance of r from the center would be simply 2 pi r, the distance, over the time. And now you can go back up here, take a look at the definition of angular velocity, which was 2 pi over capital T, and say that this is simply omega times r. So that's the relationship between linear speed and angular speed. And this only works when this angular speed is in units of radians per second. If you do it in degrees, it won't work because in degrees it's not 2 pi. So I've captured the essence of all this discussion in these equations over here. The first one is the definition of angular velocity, and it's valid in any units. The second and third ones will only give us the angular speed or angular velocity in units of radians per second. We got to remember that because that 2 pi corresponds to radians. And this last equation here only works when we use omega in units of radians per second. Okay, so we want to know the angular speed of the second hand and also the linear speed at the end of that second hand as it sweeps the circle. So now we can use our equation that says omega is 2 pi over capital T. We know that T is 60 seconds, and so that gives us an angular speed of 0.10 radians per second. And if we want the angular velocity, we just have to remember that for a clockwise motion, the angular displacement is negative, so this would be negative 0.10 radians per second. Now the speed of a bug that's sitting at the edge of that second hand sweeping across the dial would simply be 2 pi r over t. I can use that equation, or I can use the equation that says it's omega r as long as I use the value of omega in radians per second. So I'm just going to use the second form, so I get 0.10 times the radius of the circle, which is 1 centimeter, which if I convert to meter would be 1 times 10 to the negative 2 meters. So this gives me a value of 1.0 times 10 to the negative 3 meters per second, which is the same as 1 millimeter per second. So this bug would be going at a pretty slow speed, which makes sense. It's not covering a lot of distance. So I've cleared this room, and let's now discuss our grandfather clock example, and then we will discuss the Earth example. So here's our grandfather clock, hour hand, minute hand, and once again we're interested in this second hand over here. Let's say the radius of the circle that the second hand sweeps is 15 centimeters in this case. That's reasonable for the length of a second hand in a grandfather clock. Time period was still 60 seconds. That's how long it takes to go around it. And so the interesting thing here is omega, which is 2 pi over t, does not change. It's the same 0.10 radians per second if we're looking at the scalar, and a negative sign if we're looking at the vector. So the size of the clock did not change the angular speed. Both of these are going 2 pi radians in the same amount of time, so their angular speeds are the same. Let's take a look at what happens to the linear speed. So I got v is 2 pi r over t, or omega times r. And using the second form, I get 0.10 times the radius now of the circle is 15 centimeters, or 15 times 10 to the negative 2 meters. So that would give me an answer of 1.5 times 10 to the negative 2 meters per second. And this translates to 15 millimeters per second. So a bug that's sitting at the end of the second hand in a wristwatch only goes at 1 millimeter per second, but the same bug sitting at the edge of the second hand in a grandfather clock would go a lot faster. It would go at 15 millimeters per second. And that makes sense. It's covering a lot more distance in the same amount of time. Let's see what happens when I take the example of the Earth. I'm now going to look at the Earth from the top of the North Pole. So I'm sitting over here, and looking at it from the top of the North Pole, it turns out that the Earth goes in a counterclockwise manner. So that would be a positive angular displacement. And we want to know the speed of something that's sitting here on the surface of the Earth, what its angular speed is and what its linear speed is as it makes this circle. And as we discussed last time, the time period for this was 24 hours, which was 86,400 seconds. The angular speed is simply 2 pi over t, and when I put in that value of t, this turns out to be 7.3 times 10 to the negative 5 radians per second. So that's a very slow angular speed compared to our wristwatches or grandfather clock. And that's because the time period is a lot longer. It takes a day instead of a minute to cover the same 2 pi radians of angle. And finally, let's see what happens to the linear speed. So linear speed was omega times r, and that would be 7.3 times 10 to the negative 5 times the radius. So now I want this radius, which is the radius of the Earth. Call it r sub e. Radius of the Earth is 6,400 kilometers, or to convert it to meters, I got to put 3 more zeros, so 6,400,000 meters. So when I multiply that by 7.3 times 10 to the negative 5, I'll get an answer of 470 meters per second. You may be surprised that even though the angular speed is much smaller than the angular speeds of the clock, the actual linear speed is much, much bigger. And that's simply because the radius of the Earth is a lot bigger than the size of the second hands on clocks. So as you're sitting and watching this video, you're actually going around the center of the Earth at a pretty fast speed. That's about 0.5 kilometer per second, which turns out to be about 1,000 miles per hour. So hopefully this example gave you an appreciation of what angular speed is, how it's related to linear speed, and how those things change for some different examples, which might have given you some unexpected answers. And one final word about angular speed. When we have uniform circular motion, that's when the speed of the object that's going around the circle remains the same, only the direction changes. When that happens, it's going to sweep equal amounts of angle in equal intervals of time, so that leads to a constant value of omega. And once again, you can see the analogy with the linear motion here, because in linear motion we got uniform motion implying a constant velocity. So in this slice of physics, we looked at parameters like angular velocity and linear velocity as it relates to uniform circular motion. Thanks, and I'll see you later.